Yeah, okay. So welcome to the second session of today. It's a pleasure to introduce our speaker, who's Stefano Lepri from Institute for Complex System in Florence, Italy. And he's going to tell us about transport in anharmonic chains. Please, Stefano.
Yeah, hello. So I welcome everybody. Thank you very much for being here. So my talk is back to classical problems, to classical many-body problems, in particular to anharmonic chains. We all know that in statistical physics, dimensionality is important. So special constraints can change, for example, critical properties, and they also change transport properties. This is, for example, goes under the name of the long time tail problem that leads to breakdown of usual standard hydrodynamics, which is known since many decades. In this talk, I will focus on the problem of anomalous heat transport, mostly in one-dimensional classical systems. This is a topic that has been, let's say, mentioned several times during the workshop. We had also the experimental talk by Chiwei about the relevance of these ideas and topics on the problems of nanoscale transfer. So there is also, besides its theoretical motivation, there is also an experimental one. And you know that these problems are very elusive. Typically, you have to manipulate very small objects, and this is a difficult task. So a theoretical understanding is for sure important. So as far as my talk is concerned, I will first of all give a small recap, a review of what is the phenomenology of this anomalous transport. There are many experts in the audience who knows everything about this, but I think it's a good idea to recall what we're talking about. And in the second part, which is the main part, I will focus on integrable systems, integrable many-body systems, and in particular, what are the characteristic features? I will recall what the characteristic features of this integrable system from the point of view of transport, and more importantly, what is the effect of perturbation of such integrable system, the effect of perturbation on such integrable systems and on transport problems. And we consider in particular the very famous, celebrated Toda model, the one-dimensional chain with the exponential interaction, which is a well-known example of an integrable many-body system in classical physics. And I will discuss how perturbation of Toda can give some interesting results that allowed us to learn something about the integrable unit. I would also mention, as in the second part, at the end of the second part, some different class of systems which are more close, perhaps to fluid problems with these relatively new technique of multi-particle collisions that will confirm the overall scenario that I will going to present. So just very small advertising. There is this book that I edited 5 years ago, which I think is still a good starting point for those of you who want to learn about this topic and how it ranges from basic problems in statistical physics to the nanoscale condensed matter aspects that I mentioned at the beginning. So forgive me for this advertising. And now let's go to the class of models that I will discuss. I will focus mostly on these chains of nonlinear oscillators. The generic form of the Hamiltonian is written here. So imagine a set of bolts and springs as usual, or you can imagine this as a kind of discretization of a lattice, scalar lattice field. Of course, the mathematics is the same. And as you see, the equation of motion are the standard Newton's equation for nearest neighbor coupling. So this is something which is almost a textbook example. The main thing here that I will focus on being a nonlinear potential, and I will explain you exactly what kind of potential we choose. If you have periodic boundary conditions, the system is closed. For example, you have and you look for the harmonic limit, and there are two possible situations. Either this, I mean, for this kind of Hamiltonian, you have typically an acoustic dispersion of the phonons in the harmonic limit. So it's a very simple model, but it has a very rich phenomenology, as we will see. So what we're interested in is this model, and it's important to notice a fact that has been said before, that for a generic choice of the potential V, this system has three conservation laws when the isolated case, which are of course the energy, the momentum, and this quantity, which has been called in various names. For example, it's called the stretch. You can see it as a kind of density of particles, if you wish. So any microcanonical equilibrium state can be labeled by three parameters, which is this capital L. You can interpret as a length, the volume, the total momentum, which typically we put to zero to avoid the global rotations of the chain, and the energy. And associated to this global quantity, global conserved quantities, you have, as usual, local conserved densities, which in turn defines through the continuity equation the local currents. So this is more or less standard. So the example that I will, one of the examples that has been studied more is the famous Fermi-Pastaulan single model, how is this called today. So it's a very simple type of potential, model potential. It's just algebraic. So you have the usual quadratic term of the harmonic model, and then you add a cubic and a quartic term. For some historical reasons, the case in which G3 is different from zero is called the alpha beta or alpha plus beta model, while the case in which G3 is zero is called the beta model. I will anticipate that this seemingly innocent change of putting G3 equal to zero or not will change a lot of properties from the point of view of transport. So, if one wants to study non-equilibrium properties, one typically has two main choices. One is based on linear response, the usual linear response theory, which means that you can compute, for example, the transport coefficient, which is the thermal conductivity in this case, as an integral of the autocorrelation function of the associated current. This is well known in linear response. What you have to do, for example, if you want to compute these quantities in simulations, you need just a microscopic expression for the currents, which you can derive from the continuity equations that I mentioned in the previous slides. And you can use this operator, these functions in your molecular dynamics, for example, simulation, some ensemble property, some ensemble that you choose, for example, the microcanonical. And you can use this expression to compute the correlation function, the autocorrelation function, and learn about the transport properties of the system. If this correlation function decays fast enough, such that this integral can be finite for t going to infinity, then you have a finite value, and this finite value is your linear response transport coefficient. The other big line of methods that you can use is a genuine non-equilibrium method. So I think in almost every talk during this this workshop, you have seen a figure like this. So you have your system, which is in contact with two sources, two external sources, two external reservoirs at equilibrium. And you can imagine that once the system has reached a steady state, there is a net energy flow from the hot, cold reservoir, and you can use the standard Fourier law, so divide the energy currents times the effective gradient which you applied, the thermal gradient you applied, and you have an estimate of this thermal conductivity coefficient. Now the problem is that how do you model the interaction with the thermal reservoir? This is also not a matter of choice. There are several possibilities. One can use, for example, Langevin dynamics, which would be a very popular choice. One can use also more collisional type of models using interaction with Maxwellian baths, and there are several ways. But of course, the results that I'm going to discuss should be independent of this choice. So, what is anomalous transport in a one-dimensional chain? This you can see by several types of experiments or numerical simulations. I just mentioned here the most simple, the most widely used. The first one is the more direct evidence. So it's an anomalous problem. You measure the non-equilibrium conductivity with the methods that I explained you before, the non-equilibrium method. And you look how this conductivity depends on the size, on the length of the chain, the number of particles, if you wish, in double. This is just a plot in double logarithmic scale. So you see that keeping the temperature difference constant, of course, and you see that there is an increase of this, the power law increase of this coefficient, which does not saturate the finite value as you would expect for a normal conductor, normal system where transport is diffusive and ruled by the standard heat equation. Another way to look at these anomalous properties is to look at correlation functions. So look at how the correlation function decays in time, as I mentioned before. Typically what you see is in anomalous case, if you have these long time tails, so you have a decay which is like an inverse power law, and the exponent of the power law is less than 1, so the integral diverges in time, and your thermal conductivity coefficient is ill-defined. Another typical signature that has been mentioned in the previous talks is the fact that typically the solutions, the standard heat equation that you solve in the diffusive case is no longer valid, so you have to solve another diffusion to yield the temperature profile, and typically this is a fractional type of Laplacian that gives you this particular peculiar nonlinear shapes, which the singularities that Cedric was mentioning in his talks. And finally, there is a possibility to study transient processes, like how a local temperature perturbation spread in time, and to ascertain that indeed there is a spread of this perturbation which is typically super diffusive, and that you can interpret in terms of generalization of the Brownian Brownian work, which is called the Lepri work, but I will not enter too much into this. So what is important about this class of model, in order to give a description, a theoretical description of this phenomenon? So just in a very brief, let me summarize what has been learned about this system from an approach which is called the nonlinear fluctuating hydrodynamics, that's been mentioned before. So the idea is that we have these three conservation laws that I mentioned before. So this stretch, momentum, and energy. You consider the system at equilibrium and you look at the fluctuations of these three fields around some given equilibrium point. So if you write down the equilibrium, the conservation laws, you introduce an expansion of the currents in terms of this conserved fluctuation field to second order. You add noise and dissipation according to the fluctuation dissipation theory. You typically end up with a set of three coupled stochastic equations, which you can recognize to be in the same class of the famous Carter-Parisi-Zhang equation of growing interfaces, and this was put in a very clear and complete form by Alberto in his work in 2014. There are a lot of consequences you can draw from this approach, from approximate solutions that you can derive, for example, with the mode capping method. But you can derive the scaling, typically scaling relations. You can derive the typical shape of the correlation function. So that there is really a lot of information that has been derived from this approach, and in particular for what concerns this topic, you can prove that in the generic case, the correlation function of the current decays is the power law is t to the minus 2/3, so that the finite size conductivity, the finite size flux, scales to zero, like L when L goes to infinity as L to the minus 2/3, so the conductivity diverges like L to 1/3. So these results are now very solid, and they fit very well a lot of numerical observations. Yes, Cedric.
Yes, sorry to interrupt you, but I don't know, why do you say that it is some universal? Because in the nonlinear fluctuating hydrodynamic theory, in fact, depending on if the potential is even or is odd, you have different universality classes.
Okay,
so
you know too many things. No, you're right. You're right. Of course, it's universal in the sense that if I take the generic case in which this G is has some given properties, this is typically what you see.
Okay.
But you're right. Of course, you are completely right. There are situations like the situation of the beta model, for example, the pure beta model in which the universality class is different. Yes, I didn't mention this because it's a more detailed information.
Okay, thanks.
But you're right. So let me come to this problem of integrable systems. So integrable systems are very popular these days because people are studying this from the point of view of studying their transport and dynamic properties and so on. We heard something from Alberto last week. So I will deal with this famous Toda chain, which is in the same class of models that I discussed at the beginning. So the main difference is that the main feature is now that I have this exponential type of potential, and this is known since the 70s of last century, that this model is completely integrable, meaning that we have for a chain of n particles, we have n integrals of motions. So the first three of motion, the first three are just the usual ones, so this energy, stretch, and momentum. The other are just listed here, a few of them, are complicated functions of the canonical variables that one in principle can generate with the method of Lax metrics and so on. So one question is, what do we expect for transport in this system? Well, I mean, before going on, let me mention another model that I will discuss. It's called hard-point gas, which is even simpler than that. So it's just a bunch of particles and a set of particles, point particles that interact with this potential. So they are just hard-point collisions. In principle, they may have different masses. So the dynamics is just ruled by the kinematics, so you impose conservation momentum and energy, and you can compute the velocities after the collision with these simple equations. And you immediately realize that the case, as is well known, the case of equal masses is just an integrable model because all the initial set of velocities remains constant during the motion. So the only thing that happens is that two particles, when they collide, they exchange velocity, but the value of the velocity remains the same before and after. So it is indeed an integrable system. Let me also recall that in the limit of infinite energy, the Toda chain just converges to this type of model, as you can easily imagine. So these two models are also representative of two classes of integrable systems. This nomenclature was introduced by Alberto, and they correspond to interacting and non-interacting systems. So you can realize that in the case of the hard particle gas, if I just relabel the particles, so I just follow the particle that has follow the same velocity instead of just change the label of the particles, it's like having a non-interacting ideal gas. In this case, the system can be mapped exactly to gas of particles that exactly cross each other with no interaction. The case of Toda is a little bit different because it is true that when you have two Toda solitons, the two solitons are after the collision they remain the same. But it's also true that at each collision there is associated a small shift. It's called the scattering shift, which depends on the relative velocity of the two solitons. So you see also from this figure that the behavior of the quasi-particles is rather different in this case. So you see that it's not exactly a straight line, but it's something that resembles a bit perturbed motion, perturbed ballistic motion. So this distinction, as you may imagine, has some consequences on the type of transport that you may observe. Just a few comments about the Toda chain. It's a very interesting model from the point of view of linear dynamics. What is important is that there has been, of course, tons of literature on this model, but typically this is what is done is at zero temperature. So there is very little done on a chain at finite temperature with finite energy density. I refer to this recent review of Albert's phone that gives you a very nice overview of this model with a focus on this generalized Gibson sample, which is now today one of the most interesting things in the field. So what about transported in the integrable system? Just a few words just for completeness. So as I show you, an integrable system has a macroscopic number of independent conservation laws. So what do you expect? The very naive expectation, very simple expectation is the fact that you have almost ballistic excitations. You expect to have a ballistic transport. So you expect to have an infinite conductivity in a sense. Or for a finite system, you expect a conductivity which is proportional to the number of degrees of freedom. What do you expect? If you put the system in contact with two reservoirs, you expect no temperature gradient to establish, so something like a flat distribution of kinetic energy in the back of the system. And by the way, you may wonder, how do you see these properties for example, in the linear response? In linear response, this ideal conducting behavior reflects in the existence of a non-zero flux of the correlation function limit for large times. So typically, the correlation function of this quantity should go to a constant. Of course, this average now is not specified. It should be done on the GGE ensemble, so you have to specify all your chemical potentials, but the general idea is this one. So in other words, you expect that the conductivity in the Kubo formula will diverge linearly with the system size once you integrate this up to some time t. with a linear divergence. Another way to see this very same thing is to compute what they call the Drude weight. So it's the zero frequency component of the power spectrum of the current, which of course gives you the equivalent information. So in other words, you expect to have a component at frequency 0 of the spectrum that is exactly the Fourier transform of this correspond to the Fourier transform of this quantity. Let me just mention, although there are experts in this about this, that can give some estimate of this Drude weight by an approach which is called the Mazur inequality approach. It's very powerful thing, very general thing. You can give a lower bound for this limit, so the limit of a generic integral of a generic correlation function of some observable. And what is important is that in this quantity, what enters is the scalar product, so the cross correlation between your observable and the conserved quantity. So, naively speaking, if your observable, for example, the heat current is correlated to some conserved quantity, you expect to have a bound which is non-zero, and you expect to have Drude weight which is non-zero, as I said. So in a sense, you can give some theoretical estimate of these limits that I mentioned in the previous slide. This is just something that people have done. This is an example from the work of Schass and Young, in which they checked this Mazur bound with the numerical simulations, so these red points, and you see that the Mazur bound, look also the scale, it's a pretty good approximation of the real, the exact limit value of the correlation function for large times. Okay, so this is more or less what we know about. Just let me mention other things. So, what happens if you do, for example, you compute the correlation function of the heat current, for example, this J2 for the Toda chain, for the simple case of Toda chain periodic boundary conditions. So the situation is a little bit more complicated from a finite system. What you see is that you have typically, this is a power spectrum, so you see that the power spectrum has this shape, but it goes to 0 for a finite system below a certain scale, which is typically of the order of 1/n, which you can interpret as a typical transit time required for this quasi-particle to travel through the system. So you see, you have something which is still not 0. So it means that somehow there is some dynamics of quasi-particle carriers, because this is an interacting interval system. So there is a form of randomization of your initial data due to this solid motion. And this is just involves what I showed in the previous figure. So in a sense, this has been called, for example, non-dissipative Soliton diffusion, in the sense that despite the system is indeed integrable, there is a sense, due to the fact that it is an interacting system, the stochastic sequence of spatial shift experienced by the solitons gives some form of irreversible behavior. So the situation is a little bit more rich than one would expect for naively for example, a simple ideal gas. Okay, so now let me come to the core of the cell. So what happens? We know that this. I explained what are the main features of this integrable system, which are certainly interesting. But of course, one would argue, what happens if I perturb very little an integrable system? So are these features, where the features of the integrable system persist, or do they disappear, or the scenario is even more complicated? So based on the very general ideas, based also on this fluctuating hydrodynamics idea, we may expect a couple of situations. No? If I perturb this H prime such that all the conserved quantities except energy are destroyed, so something which is which removes all the conservation laws, we expect to have a standard diffusive behavior, because we know that systems with a single conserved quantity generically have a diffusive type of spreading of energy. If, on the other hand, this H prime destroys all the conserved quantities except the famous three dimensions, so for stretch, momentum, and energy, based on this general consideration, one would expect to have an anomalous behavior in the universality class of KZ, possibly. So one would expect to recover the standard scenario, for example, of the Pastel model or similar instances. So in the following, I will just show you that this is indeed what happens, but there may be some peculiar things that happen that deserve to be understood. So first of all, let me start with the first case. So suppose I take a situation in which the perturbation destroys all the conserved quantities, presumably, except the energy. One example that has been studied in the literature is this one. So it's what we call the pinned Toda chain. So I just add an external field, if you wish, of this form. This Z is just a value, a positive value that can be 1, 2, 3, 4, for example. This model has been introduced by Joel Lebowitz and Scaramazza, and they observed some peculiar features that I will now discuss. So in this case, in this figure, I just give you an intuitive idea of what is happening in this model. On the left side, you have the standard Toda. On the center panels, you have the pin Toda with the Z equal 2, and on the right, you have the pin Toda with Z equal 4. So in the first row, I just depict the situation in which you start with a localized bunch of energy at the middle of the chain, and you just look in the space and time how it propagates. In the second row, second line, you see a situation in which you have just a random initial condition. So you see that in the case of Toda chain, you see what you expect. You generate a couple of these localized solitons that propagate, they just move almost ballistically, they just interact a bit with the scattering the dimension, but after all, I mean, they remain there. On the opposite case, when Z is equal 4, the situation is very different, because you see something that the energy is just spread like in a standard diffusive process, and it tends to disperse throughout the system. You see it's very similar also for random initial condition. The situation Z equal 2 is somehow intermediate between these two situations. So it's a strange situation in which you still preserve some form of quasi-ballistic motion. It seems very clear in the. So one may expect that these features that you see qualitatively in these pictures may reflect in transport problems. So how do they reflect? They reflect in the following way, by displaying very strong finite size effects in the non-equilibrium simulation. What do I mean by this? For example, look at this temperature profile. So this is the average kinetic energy in the steady state for several different sizes. And you see when the system is pretty short, so you can take, for example, this yellow line. The system is pretty short. You have an almost flat profile, which is something which you would expect for a ballistic conductor, as I said. In order to see the typical gradient forms with the linear shape with respect from Fourier, from the Fourier law, from the standard heat equation, you need to go to very long system, right? So of the order of a few tens of thousands. And in the very same way, in order to see the typical scaling 1/n of the flux that you expect from standard diffusive conductor, you need to go to very large system. So what is the thing that we learned from this example? Is that the type of perturbation is important. So despite the fact that the system will be in the thermodynamic limit a diffusive one, for very finite systems, you may observe the different type of situations. And this is, of course, something a priori is not expected. And honestly, I don't know exactly what is the reason why this specific form of the perturbation is different from the other. Even more, if you look at the correlation function or the spectrum, like in this case, of the current, of the energy current, as I say, this is what you study in the green cube approach. What you see is for this Finite-temperature chain, the situation is rather peculiar because this spectrum has a very large range of frequency. It displays a typical power law behavior, and then it saturates at small frequency. So it means that there is indeed a very strong correlation surviving in this model, which you don't see when you take, for example, the case with the pinning, which is with z equal 4. So for example, if you look at the blue curve, the spectrum in this case is definitely more similar to a Lorentzian, so it's something which corresponds to a very fast. So the moral of the tale is that that somehow some perturbations can indeed preserve a strong correlation in the system, for reasons that I actually do not know yet, but can still preserve this correlation and give rise to transport, which is strongly correlated on a very long time scale. But I confirm that in any case, this system remains diffusive as expected from the general arguments. So now let's turn to the other case. So the situation in which instead of destroying all the correlation, all the conserved quantities except one, I preserve the three fundamental conservation laws.
Sorry, yes? Stefano, yes. Can I interrupt you?
Sure.
In the previous slide, there is this omega 503.
Yes.
And minus 503. Yes. Where it comes from? What does it mean?
I don't know. Just numerical observation. Looks like Kolmogorov spectrum in turbulence, but I don't think that has nothing to do with that. Although
but it is not some prediction of the of the nonlinear fluctuating hydrodynamics.
No, because in this case, nonlinear fluctuating hydrodynamics, it's exactly should be the diffusion behavior, right? In the long time. So this is something that is somehow on intermediate scales. I guess it should be related to the fact that these solitons in this are perturbed and they interact in some way that gives these long correlations.
Okay. Okay.
So let's go to the case in which you just consider perturbations with that preserve the three fundamental conservation laws, and I will discuss two classes of perturbations. The first one is to take the Toda model or the hard particle gas with slightly different masses. So this, as I mentioned, will you can understand this very easily from the hard point gas, because if the masses are not equal, not exactly equal, there is no exact exchange of velocities to the kinematics. So you have some form of interaction that renders the system non-integrable. One possibility is to take, for example, the diatomic arrangement. So you take the even particles to have a mass 1 minus delta half, and the odd particles to have the masses 1 plus delta half. I recall you that the particles do not cross each other in all these models, so the order is preserved. So the even and odd particle keep this alternating order for all times. The other case that I will consider is the so-called conservative noise. Conservative noise is a very interesting type of process. It's random process that has been introduced to study anomalous transport in this model. So what you do Typically, you take the total dynamics and you add random collisions that just at random times exchange the momenta of a couple of neighboring particles with some given rate. Okay, so you can immediately understand that this process is called conservative exactly because it conserves energy, because the total kinetic energy remains constant. It also conserves momentum because exchanging the velocities of two particles, the momentum of two particles doesn't change the sum of the. So there is a lot of things that you can do with these models since they are amenable of a lot of analytical calculations. So we thought to follow this route because it's a way to introduce a form of interaction which is very convenient also for numerical simulations. As I said, in both these cases, the tree conservation law remains. And presumably all the other are destroyed. And the two parameters delta and gamma, respectively, controls the effective interaction between the quasi-particles that I call velocitons for the HPG model and solitons for the. So I have now two systems that I can study with the equilibrium and equilibrium methods. So what do I see in the for example, in the diatomic Toda chain? I repeated that in this case, according to standard arguments of the thermodynamics, I expect a diverging and anomalous behavior with the thermal conductivity exponent that diverges, with the thermal conductivity that diverges at L to 1/3. So if I take, for example, a system which is very much perturbed, so take this delta equal 1, this green line, you see that after an initial ballistic growth, there is a tendency indeed to go towards this expected behavior. So a strong perturbation will indeed turn the system in the standard case of KTZ universality class. So far, so good. So we are happy with that. But look at what happens when I decrease this delta. So I go closer and closer to the integrable limit. So I go from delta equal 0.5, 0.3 up to 0.07. You clearly see that there is a tendency of this quantity that you can easily, at least visually, interpret as a convergence of this quantity to a constant. So what happens here? There is a model which I expect to be anomalous on the basis of the conservation laws, but I see a regime in which I have this saturation. So what's happening? So my claim is that actually what you see in this system when you approach this integrable limit is that you have actually three regimes. The first regime, which is ballistic, so which corresponds to the fact that the system is too small. Then there is an intermediate diffusive regime. And finally, you will observe the anomalous regime corresponding to 1/3 growth. So in other words, this curve, when you approach the integrable limit, should increase linearly initially, then it should be almost constant, and then it should grow again like L to 1/3. This is my claim. So we have what I call this size-dependent transport regimes. So this is just the same thing that I said before. What are the typical scales of these regimes? Let me just give you a very physical, simple argument to understand what is happening. So the fact that you have a length-independent flux, so you have ballistic transport, is due to the fact that the quasi-particles, for example, the solitons for Toda or the velocitons for the APG, have a very long mean free path with respect to the size of the system. So if the mean free path is larger than the size of the system, you typically observe ballistic behavior. This is a very standard thing, and everybody will agree on that. So the problem is that when you are close to the integrable limit, this mean free path of quasi-particle will be very large because perturbation is very small. Okay? So So in principle, you can have three regimes. One is the ballistic. Then there is a diffusive situation in which the mean free path is small with respect to the system size. But yet you are not in this hydrodynamic regime, because the hydrodynamic regime will require that you have indeed effects on an even larger time scale. I denote this length scale. I denote this length scale del star. So I expect to have three regimes if these three characteristic lengths, so small l and L star, are separated enough. So it is possible that these scales are separated enough. Okay, let's look at a more quantitative point of view. So suppose that you have your heat flux, and suppose you decompose this into terms. So if you call epsilon the perturbation parameter, so the quantity that measures how far you are from the integrable limit, you assume that you can separate your heat flux into terms. One is called the anomalous term, so the one that you expect to comes from this nonlinear perspective hydrodynamics type of interaction, and then a normal one, which could be kind of diffusion type. So, by the way, I think this should fit pretty well to the work of Keiji Saito when he speaks about bare transport coefficient and renormalized transport coefficients. And so I think I'm not able to do it very neatly, but I think it's the same kind of concept which I learned from this talk. So the idea is that you can give some a priori estimate of the dependence of these quantities based on what you know about the diffusion and anomalous diffusion. So the normal part, one could say, okay, let's look in the kinetic theory books, and we know that in this case we expect to have something of this form. So a scaling that you can fit with this kind of expression, that you see that when the mean free path becomes the size becomes very large with respect to the mean free path, it goes like small l over L capital L, which is the standard scaling of the flux for the diffuse system. On the other hand, for the anomalous part, we expect this famous one-third exponent of the KTZ class. So you can estimate this to be of this type. I use this eta as a generic exponent, but what I will consider eta to be one-third. So the problem is,
sorry,
yes.
What is R in the
okay, yes, again. R you consider as a kind of measure of the boundary resistance. So it gives you the crossover from ballistic to diffusive behavior. Just a phenomenological parameter.
Okay.
So what you can compare the relative size of these two terms. So if you assume that, for example, that all these, when epsilon goes to 0, this mean free path becomes very large, and you introduce an exponent theta that gives you the typical behavior of the mean free path with epsilon. This will be model dependent, of course, because it will depend on the type of interaction among quasi-particles. But let's assume for a moment that this is the typical form. You can try to plug these notions into the first line and try to estimate which is the typical length that gives you a crossover between this diffusive and anomalous regime. So let's write the same equation in this way. So you introduce these CA and CN as two parameters, two prefactors, the lengths in these scaling arguments. So if C of A is not singular, so assume that the C of A remains finite for epsilon goes to 0. Let's make this assumption. And you compare these two things, you immediately see that there is a crossover length where the anomalous part dominates, above which the anomalous part dominates the diffusive part. So typically this will be given by an inverse power law with some exponent theta beta is 1/3. So it will depend on this point theta, which, as I said, controls the interaction among quasi-particles. Yes, Cedric?
Sorry. Do you have some way to estimate theta, even if it is model dependent? Do you have some
next slide. Next slide.
Okay.
Okay, next slide. Let's see if we can give some estimate of this theta for the models that I described. Yeah? Let's start with the R point gas. So if you work a little out the kinematic expression for that I wrote in the previous slides. So you write down the equation of motion. In the limit in which the mass difference is small, you can derive an effective Langevin equation for the particles. It is an approximation, assuming that the particles have two-body interaction, but nevertheless, one can hope it gives some insight on the actual proof. So what comes out? It comes out that the typical mean free path from this Langevin equation is, of course, of the order 1 over delta square. There is actually tau, which is the typical interaction time, but you can assume that this is a finite number. So in this case, one could argue that theta is 2. What about the diatomic Toda? Well, this is much more complicated, but okay, the atomic Toda and the limit of high energy, very high energy, is very similar to the R point gas, so perhaps an estimate of the same type could not be too wrong. So we may argue that probably the interaction could be, the effective mean free path should scale like 1 over delta T square. Finally, the Toda model with conservative noise, well, there is a typical parameter, which is the rate at which I perform the collisions, the random collisions. So I would say that the mean free path should scale like the inverse of this rate. This could be a simple estimate. So in any case, for all these three models, you see that if you plug these results into this formula, you immediately see that the L star can be much larger than L, can be of order of something like 1 over delta to the 6. So indeed, there could be a very wide separation of these scales that justifies the idea of the observation of this intermediate diffuse equation. And this works pretty well with the numerical simulations. These are the simulations for the three models that I described you. I think it's time to go to the end, so it works pretty well. You can do even better. You can try to test the idea of the decomposition of the flux into terms. For example, you can compute the anomalous part fitting the normal one, and you see that the scaling that you observe is very good agreement with the prediction of this 1/3, 2/3 actually, because it's plus. So, as a byproduct of this analysis, you have also very good verification of the prediction of the anomalous exponents. So finally, what happens, for example, for this FPU model in the alpha plus beta? There is a quote by my friend Giancarlo Benettini that I like to state that the FPU alpha plus beta is tangent to order 3 to the total model. What does it mean? It means that if you go to very low energies, the Fermi-Pastor model alpha plus beta is very close to Toda. And this has been proven in many different ways. For example, if you perform the standard equipartition experiment. So based on what I've said before, what would you expect for the FP model? Well, you would expect the same scenario as a perturbed Toda, because you may look as the alpha plus beta model as a Toda with some perturbation that is added to it. And indeed, this fits pretty well. These are data by Abhishek and his group. It fits pretty well with the numerical observation, because you see that when the temperature goes to 0, so when you approach this integrable limit, you start to see exactly the same scenario as in the perturbed Toda. So my claim is that even for alpha plus beta model, you do observe these three regimes. This explains a lot of numerical observations, I guess, that were made in the recent year that claim that there is indeed a finite conductivity in this model, which I would conclude to be just a signal of this intermediate diffuser regime close to the integrable. Finally, well, you may say, okay, you said a lot of things about Toda integrable model, but we have a much simpler integrable model with the nodes, the harmonic chain. So what happened for the harmonic chain? Okay, for the harmonic chain, you don't observe. If you take the harmonic chain plus a perturbation, which is, for example, the case of the Finite-temperature model beta, so the case in which you have the quartic interaction, you don't observe any intermediate diffusive regime of energy. Why? Well, I don't have a general answer, but I can give you an answer for the case that we studied together with Carlos many years ago, so the case in which we have the harmonic chain with conservative noise. In this case, we can indeed prove that this coefficient CA that enters in this estimate, so the coefficient CA that enters in this has a peculiar behavior with the perturbation parameter. So it is also diverging the perturbation parameter. So this kind of estimate does not hold anymore because even CA depends on epsilon, this language. So it means that if you do the math, these two characteristic length scale, they cannot be separated as in the case of the alpha plus beta model. So in this case, you do not observe the diffusive regime. So finally, is it everything related to the fact that you consider these harmonic chains? No. We have very good evidence that the same scenario holds, for example, for the multiparticle collision fluid. I don't have time to explain, but the idea is very simple, is that you consider a many-body a gas in which the nonlinear interaction is just replaced by some random collisions done in some boxes. This is a very interesting class of models for doing simulations of fluids, for example. And then if you look at the one-dimensional MPC fluid, you see exactly the same phenomenology when you are close to the integrable regime in which the mean free path becomes very large. So this is not just related to the fact that you have this harmonic chain, it also works for fluids, for general fluids. Finally, last slide. Does it work also in higher dimensions? So this is work that we did recently with the Rongxiang Luo. Yes, it works also in this case. If you take, for example, the MPC gas, the MPC fluid in a slab, in a simulation box which has a very large aspect ratio, so you have a situation in which you have, we imagine, have a bar with some length L and cross-section area W. If W is small enough, so this is quasi one-dimensional, but the particle move in 3 dimensions, then you indeed see the same scenario. So crossover from ballistic to diffusive to anomalous regime. So we believe that this could be relevant, and I come to the conclusion. And the main conclusion is that this anomalous transport on the, especially the one in KPZ universality class, is indeed a generic phenomenon. Now that it's very solidly, very solid the evidence. And the problem may arise when you approach the integrable limit. So in the integrable limit, there may be some complications. The main complication, as I said, is the possibility to have this intermediate diffusive regime. That on a finite scale may lead you to conclude the system is diffusive, but my claim is that this is not the case. So you may need to go to even larger sizes in order to see these hydrodynamic effects. And what is also important is the fact that the type of underlying integrable model matters. So if I take the FU alpha plus beta, which has an integrable limit as the Toda chain, is different from the beta model, which has a limited harmonic chain. What is important is that you still see this kind of phenomenology, also include models with three-dimensional dynamics, which I think is very important for the possible experimental observations of this effect. And finally, I just mentioned here the list of papers, mostly to mention the people who collaborated with me on this topic in the recent year. Thank you very much for your attention. I stop here and I'm welcome for questions.
Thank you, Stefano. Thank you. So are there questions? Yeah, Abhishek, go ahead.
Hi, Stefano.
Hello.
So, so how does one understand this within the context of fluctuating hydrodynamics? I mean, so like this crossover, I mean, this of behavior from diffusive to anomalous at some, so it looks like if we look at these correlation functions, I mean, so for example, you have this, so the fluctuating hydrodynamics, what you expect is that you should have these two sound peaks with KPZ scaling. But here it's, so I guess somehow one expects that for a long time you see just a diffusive peak, and at long times maybe it goes over to these two KPZ peaks, right?
Yes.
So, but I mean, I don't see how within the context, framework of hydrodynamics, how exactly does this come about?
I think it's just like in the standard situation. So there is a kinetic regime in which the system thermalizes locally and is ruled by this mean free path. And the KPZ, the hydrodynamic regime, is on scales which is much larger than this. And I think it's very similar to what Keiji presented. So you should have an intermediate regime in which this bare transport coefficient dominates. Then on much longer time scale, you should see the normalized one. This, I think, is the scenario.
Sorry, yeah. So,
no, okay, go ahead.
Yeah.
No, so I mean, so let's say from the non-equilibrium simulation, you see that the diffusion constant saturates to some value for a long, and then after very long length scales, it blows up.
Yeah.
So the saturation value should probably be the bare transport coefficient, right?
Exactly. It's very close to the one we would estimate from naive kinetic theory.
Okay, so I guess
so somehow that if you have a gas, it's the mean free path times some typical collision time.
Right, yeah. Okay. So
very close to that.
Right. Okay. Yeah.
So after all, is what is written in textbooks, no? Right? In order to see the hydrodynamics, you have to go to a scale which is much larger than the typical thermalization scale. So if you go to close to the integral limit, this scale becomes very large. It can be 1 over delta to the 6th, like in the case of the Toda model, the diatomic Toda model.
Okay, so I mean, so do you also have like simulation results for the correlations functions where you see this crossover?
Sure.
Oh, is it okay? I don't know if you didn't show, right, in the.
No, I didn't show it. I haven't in the paper.
Okay, so you do see this exactly the same crossover in the correlation.
Yes, for example, for this 3D MPC, there is clearly a change from an exponential decay to a power law decay.
Okay.
It fits very well with the non-equilibrium simulation. So.
Okay, yeah, thanks.
Yeah. Cedric?
Yes. It is related to the question of Abhishek. In fact, you have this crossover between the 3 different regimes, between ballistic, diffusive, and anomalous. And do you have some theoretical argument to predict how to quantify this crossover? How to pass from one regime to some other ones, or maybe numerically you have some.
The argument that I gave you, it's more or less a scaling argument. So it's just, I think everything depends on what is really important is how the quasi-particles interact. So what is a typical scale for interaction with quasi-particles. And another thing that you have to know, and this probably is important also for you, is you need to know a bit about these prefactors, so this CA, because also
but
this
CA is just a constant. It is,
yes, it is a constant, and it may depend on the perturbation strength, right?
you mean it's a function of epsilon?
Yeah, it could be a function of epsilon. For the harmonic change, this is what happens. For the Toda, it doesn't seem to depend because the arguments are consistent. But I don't know how to estimate that real. Or this CN could also depend on epsilon.
Okay.
Without a precise information on the prefactors, it's not obvious how to do prediction. You can assume that they do not depend, but we have a situation in which they depend. So.
Okay. And even in the case where you have some stochastic noise, it is not easier to predict something, because we had some paper in which we consider some harmonic chain, in which you have the harmonic chain plus the exchange noise.
Yeah.
And so if you don't, and you put some parameter in front of the harmonic potential. If the harmonic potential is a parameter in front of the harmonic potential is 0, then you have some diffusive behavior because you have just the noise. You agree?
Yeah, but the situation will be the situation which for infinite chain you have an anomalous behavior.
Yes, but okay, if you have just the noise without the harmonic interactions, you don't have any anomalous behavior. It is just a normal behavior. And when you have some intensity which is of order 1, then you have some anomalous behavior, which is Phys Laplacian, fraction Laplacian 3 over 4. And then we can try to interpolate between the two regimes. And what we did is that you observe that we can prove it, that there is some transition at when it is a function of the scaling parameter, but there is some critical exponent which is 1/3, in which you observe some transition between the anomalous behavior and the diffusive behavior. And I would like to know if it is for the harmonic chain, but for the anharmonic, for the Toda lattice, for example, could you have some predictions like that? So you consider the Toda lattice and you put some parameter.
For the atomic chain, the atomic Toda, I would expect is mean free path to be of the order of 1 over delta square.
Yeah, and in the case where you take the Toda with some stochastic noise, do you have some predictions?
I would expect 1 over gamma. It works pretty well. But,
Okay. Okay.
This would be the very naive thing. No, the mean free path is of the order of the rate with which you apply the perturbation.
And all these
things
are in your papers?
Sorry, Cedric. Maybe
sorry.
Yeah, but it's late.
It's going a bit too long.
Okay.
Yeah.
Just is it in your papers? The mention?
Sure.
Yes.
Yeah.
Okay. Thanks. Sorry.
Yeah, also because people are leaving. So maybe Anupam wants to ask the last question.
Yes. I would like to make a remark that Stefan, we have also seen similar diffusive to anomalous crossover in a 3-particle collision model. So it's a stochastic model, 3 particles which are stochastically colliding at some rate.
Yeah.
And there, because of we know the stochastic, this is a stochastic model, so we know the Baire transport coefficient in the hydrodynamic equations. So, if you look at the nonlinear fluctuating hydrodynamics theory and look at the correlation function, then in the propagator you will have exponential minus k power mu t, and then also you will minus k square dt. So now at small lengths, the diffusion term will dominate, and at some point you will see a crossover. So we see the non-equilibrium crossover. So we see a j by delta t by L. That crossover we see from 1 over L behavior to 1 over L to the power 1/3 behavior there. Yeah, but we did not look at the correlation function.
Yeah. No, I think it's the same thing. What was more interesting to me is the fact that when you approach the integrable limit in the deterministic model, like a few, what you observe is really a signature of integrability.
Yeah.
Of course, when you have stochastic perturbation, you can control the interaction in some way. But even there are some subtleties because
Certainly. Yeah. Okay, thank you.
Okay. So, yeah, it seems there are no more questions from the audience. So thank you again, Stefano, for your interesting talk.
Thank you very much.
Well, this was our last talk for today, but we continue tomorrow, same time. So have a good day, everyone.
Thank you, Stefano.
Ciao, grazie, ciao. Bye.
Send you an email.
Bye.
Ciao.
Bye. Bye.
Alberto. Ciao.